Hello and welcome guys, this is Gopher Dudes, and in this video I want to teach about computers and how they work. Also want to teach about number systems, memory types, and so much more. So I'm super happy and excited about teaching you all of these concepts. So without further ado, let's go ahead and jump right into the lecture. So first I want to start talking about how computers work and what exactly I mean by how computers work, because pretty much every kid out there knows how computers work. So let's go ahead and jump right in. How computers work? That's a very bizarre and very abstract question. I want to tell you that computers work based on electricity. So they run on electricity, and that's super important for you to understand. Wow, that's super amazing. Really? I mean, even a kid knows that they run on electricity. I mean, what else they can run on? Of course they run on electricity. They don't run on water or something like that. So what if there's no electricity?
What if there's no power?
That's a good question. If there's no power, there's no computers, but they do run on electricity. Computers also are made of circuits and switches. And what that means is when you're checking your email, when you're visualizing an image or a movie, or when you're visualizing a website, it really means it all comes through the energy, through the circuits. Those circuits create the state which the computer needs in order to render those things. So that's super important for you to understand. And these are two key concepts. I mean, it is stupid and it is obvious, but they do run on electricity and they do function based on circuits and switches, and they really are made of those kind of things. So the next thing I want to talk about is state representation, and what that really means is computers are on or off. Man, you keep telling us a lot of obvious things. Of course I do tell you a lot of obvious things, because without me telling you these, you won't be able to understand a couple of concepts which I think are important for you to understand. If this section is too easy for you, you could just skip it and come back when I start doing something more interesting. But if you guys want to understand what a lot of developers don't understand or aren't even aware that these things exist and they use it day by day, then I don't know, you could skip this section. So we want to talk about state representation. So what exactly state representation means is, I told you, it's on or off. So your computer is on or it's off. So basically it has two states, on or off, it's powered or not powered. So that's pretty much it. So another thing I want to talk about are number systems. And I promised you we're going to talk about number systems. So what exactly are number systems? Now, electric circuits are nice, but we can't really make assumptions based on those things because they're electricity and stuff like that. And for many of us, including me, this is magic. And we don't make assumptions on those things. We make assumption on numbers. So numbers are easy to play with, are easy to manipulate, and that's why we play with numbers and we make assumptions on numbers. We represent state on numbers. So it really means the state on or off is represented by numbers, and you probably know which numbers, 0 and 1. But we're going to talk about those two. So the first number system I want to talk about is the binary number system, and what that really means is the fact that binary really means 2, like base 2. And why is it binary and why is it base 2 and what exactly a base is? We're going to talk about what a base is. So it's binary because it has two states. It's 0, 1, on, off, and stuff like that. So what exactly a base is, because binary is base 2. So a base really means how many digits a number system has. So for example, base 2 or binary system means it has 2 digits, and that's 0 and 1. So the next number system I want to talk about is the octal number system, and it really means it has 8 digits, as I said with the binary one, 0 through 7. And why 0 through 7? Because we start from 0. So we 0 through n-1. Another number system I want to talk about is base 10, which is the far most common base used, is the most widely used number system, and those are decimals. Those are numbers which contain digits from 0 to 9, and we use them every day, and I don't have to explain that because you guys know that, and that's pretty obvious, right? Decimal number system really means it has 10 digits and it's base 10 also. So all of these words are interchangeable: base 10, decimal, 10 digits, so they all really mean the same thing. So another base I want to talk about is base 16, which is also widely used in computers, and it really means it has 16 digits. Nah, not really. Symbols. And why not digits? Well, it has 10 digits, it has 0 through 9, and it also has letters, has 6 letters. So 0 through 9 and A, B, C, D, E, F, which is the list of symbols to represent this type of system, this type of number system, which is widely used in computer science. So this one is called hexadecimal. So let's recap. So we're going to talk about binary, octal, decimal, hexadecimal. So we're less going to talk about octal. We're not even going to touch that, but we're going to talk about binary, decimal, and hexadecimal. So another thing I want to talk about is the decimal system. Decimal system seems pretty obvious, right? I mean, it has human understandable values, something like 80K a year for a programmer salary. I mean, that's pretty reasonable, right? It also has easy to use and remember values, something like John owes me $50. It's easy to use. It's Easy to remember that. Also, easy to perform certain operations on. So if we, for example, want to perform calculations, that's also easy to use. I mean, it's decimal, right? We use it every day and it's pretty obvious. So something like 21% taxes for a $5,000 salary means 5,000 multiplied by 21 divided by 100, which is 150 bucks. I mean, that's pretty interesting about the decimal system. We never ask questions about it because we use it so naturally and we use it every day. So another number system which I want to talk about is the binary number system, and that's the far most widely used system in the computers. And why? Because computers only understand binary. They only understand zeros and ones because computers run on electricity and they are made of circuits, right? So we're coming back to the things we talked about, which were obvious in the beginning, but now they make total sense. So basically, this is also called the computer language. So binary means on or off, as we talked about. So binary really means on or off. It also means 0 or 1, or it could mean true or false, or it could mean state 1 / state 2. It really is something which represents a state. All of these words are interchangeable and they could also be called a bit. So a bit really means a representational unit which represents a state. I know that sounds creepy, but really represents state inside our machines, our computers. So let's have a quick look at an example. For example, 117 in base 10 is equals to 01110101 in base 2. And what on earth that really means? I mean, how did I get to that example? How did I get to that result? So let's go ahead and take a look at that. So basically, we have this long number 01110101. So how exactly we represent that? Well, basically, we need to make some calculations before we start converting a number into binary. So the calculations are pretty simple. If you've raised numbers to a certain power, that should be pretty obvious, pretty easy, and easy to grasp. So basically, we raise the base to the power of 0, to the power of 1, to the power of so on and so forth until we get to the power of n minus 1, which in case of a byte means to the power of 7. Why 7? Why from 0 to 7? Well, because that's 8 bits, right? And we said that 8 bits is a byte. We can also have more than 8 bits, but we're going to take this simple example in order for you to understand. So after we've done those calculations, we start putting zeros and ones in those squares. And we'll start with the first bit, which is 2 to the power of 7. And that's 128. So the question we should ask ourselves before completing these squares of zeros and 1 is the following. Is 128 less or equal to 117? No, then we put a 0 there. Is 64 less than equal to 117? Yes, then we put a 1. Is 64 plus 32, which is 96, less than equal to 117? We put another 1. So again, the same question. Is 96 plus 16 less than equal to 117? Yes, we put another 1. And we keep asking the same question until we complete all of the squares. So basically, we complete the squares of zeros and ones until we get to the last bit. So basically, if we want to take this number 01110101, and we want to make sure that this is the number which we converted from 117 and this is the right representation, we should do the following. It's a pretty simple exercise. So basically, we take the value from each square and we multiply it by the value represented by that bit. So we take the first bit, for example, it's 0, 2 to the power of 7, which is 128, and it's of course 0. And then we take the second one, which is 1 multiplied to 2 to the power of 6, which is 64, plus 1 multiplied to 2 to the power of 5, which is 32, and we sum it up until we get till the end. And then we sum these numbers up and we get 117. All right, so another system I want to talk about is the hexadecimal system. So basically, hexadecimal system is used to represent big numbers like memory address, for example, and stuff like that. So it's pretty interesting that hexadecimal systems are pretty much used for representing big numbers, big things in general. Also, let's have a look at a real quick example. So we have 2FE in hexadecimal, and this equals to 766 in decimals. So what on earth is happening? How did we get to that number? So let me go ahead real quick and explain you. So basically, we primarily use two operations here. So we're going to use division without remainder, which you probably are familiar with. So you basically divide the number and you don't take the remainder. So for example, let's take 25. So 25 divided by 2 is equal to 12. It's not 12.5, which you may expect. And that really means division without remainder. So another operation we're going to use here is the modulo operation. So this really means remainder of division. So basically you take the result from the previous operation, for example, 12. So we say 12 multiplied by 2. And why by 2? Because we divided by 2 in the previous operation. And if we take 12 and multiply it by 2, it's equals to 24. So basically, now we have 24. So 25% 2 or 25 modulo 2 really means 25 minus that result, 24, which is 1. So 25% 2, it's equals to 1. And that's the remainder of division. So these are the operations we're going to use in this hexadecimal system. So let's have a look at the example. First operation we do is 766 divided by 16. And remember that this is without remainder. We do not take the remainder into consideration. So 766 divided by 16 means it's equals to 47. So then we do the same thing, but we apply the modulo operation. 766 modulo 16, it's equal to 14, which in hexadecimal representation, I said it's E because we have letters, we have digits, and we have letters as well. So we do the same step over and over again, but the question is, when do we stop? So I'll tell you when do we stop actually. So we do the same step. So 47 divided by 16, it's equals to 2. And 47 modulo 16, it's equals to 15, which in hexadecimal is F. And we do the same step, as I said, until some condition. So that condition is when the n number divided by 16, it's equals to 0. So when that is equals to 0, then we stop. So 2 divided by 16, it's equals to 0. And 2% or 2 modulo 16, it's equals to 2. And we have 2. So 2 in hexadecimal representation is also 2. Then we assemble the number. And how exactly we assemble the number? We assemble it from the reverse order. So we have 2FE. So now that we got from the decimal number to the hexadecimal number, question is, how do we get back? How do we actually check that that number is actually converted the right way? So this is a very simple operation as usual, and it's very similar with the binary one which we did previously. So we basically take each symbol starting with the last one, and we basically multiply that to the base, to the power of n-1, and so on and so forth until we get to the power of 0. So while that sounds complicated, it's really not. So we're basically going to do the following. We're going to take 2 in hexadecimal. So 2 from hexadecimal in decimal means 2. So 2 multiplied to 16 to the power of 2 plus F, and F in decimal means 15. 15 multiplied to 16 to the power of 1 plus E. E in decimal is 14. 14 multiplied to 16 to the power of 0, which is 1, and which is 14. So this one summed up in the end gets 766. So you can check it out. All right. So while we played with the hexadecimal system and the binary system and all others, all of those examples were very specific. Now, I prepared some generalized formulas so you guys have a general idea of how to compute these numbers, of how to convert these numbers into any base, from 10 to any base and from any base to 10. So we're first gonna have a look at how to convert numbers from base 10 to any base, to base n. All right, so this is a generalized example, so don't sweat it, don't make it complicated, because we're gonna dive into examples as well. So you're gonna see that it's not that complicated, it's fairly easy. So the basic idea here is we do two operations, and we talked about them. So basically we do division without remainder and the remainder after division of those two numbers. Let's have a look at what those constants mean. So basically n means the decimal number, which we on every iteration divide and do modulo operation on. And we have the b, and what exactly is the b? Is the base, and we talked about what a base is. So basically on every iteration we do that operation. N is equal to n divided by b, and that is without remainder. And we also do this until n divided by b is equal to 0, and that's our stop point because we have to stop eventually somewhere. All right, so let's have a look at a more concrete example. How do we apply this formula in practice? So let's say, for example, we have the number 823, and that is in decimal, and we want to convert it into hexadecimal. So how do we do that? We apply this formula until we respect those conditions. So the first step is we take 823 divided by 16, and it's 51. Then 823 modulo 16, and it's 7. So 7 in hexadecimal, it's also 7. And then we take 51 from the last operation, we divide it by 16, it's 3. And 51 modulo 16, it's also 3. And in hexadecimal, it's also 3. And then we take 3 divided by 16, and it's 0. So this is the stop point, right? And we also take 3 modulo 16, and this is 3. And in hexadecimal is also 3. So now we can assemble the number in the reverse order as we mentioned. So it's going to be 337. So 823 in hexadecimal is 337, right? I mean, what's the difference? It really looks like decimal, right? It does look like decimal, but it's hexadecimal actually. So while this example was quite simple, we only had to do 3 steps. Let's take a look at another example when we convert a number from decimal to binary. So as I said, we convert from decimal, from base 10 to any base. So in the first example, we converted from base 10 to base 16. In the second example, we're going to convert from base 10 to base 2. So we have the number 25 in decimal, and we want to convert it to binary. So let's apply the same formula and see how easy it is to do that. So we have 25 divided by 2, it's 12. And remember again, this is without remainder. And we also do 25 modulo 2, which is 1. And we do the same operation, and we do 12 divided by 2, which is 6. And 12 modulo 2, which is 0. And we do it again, 6 divided by 2, which is 3. 6 modulo 2, which is 0. 3 divided by 2, which is 1. And 3 modulo 2, which is 1. And we do it again, 1 divided by 2, which is 0. And 1% 2, which is 1. So now that we got to 0, how exactly we represent this number in binary? Because we know that a byte, it's 8 bits, but here we only have 1, 2, 3, 4, 5 numbers. So how exactly we do that? Well, it's fairly simple. We just complete with zeros. So So then we assemble the number and we're gonna have something like 00011001. And that's pretty easy. I mean, we just apply the formula which I came up with. Now, that's my own formula. It may not be the best explanation, but I tried my best. So let's have another look at the generalized example, because I said we want to convert from base 10 to any base, and we also want to convert from any base to base 10. We want to be able to do those two operations, and let me go ahead and explain the second formula for you. So basically we have that weird sign, which I know you guys are gonna hate me for that. That's just a mathematical sign, which really means the sum. But I wanted to make this as clear and as short as possible, so that's why I used that sign. So it really means we loop from the last element, which is n-1, to the first element, and for every element in that array, in that collection of symbols, in this case, we multiply them by b, by the base, and their base is raised to the power of absolute value. And in the absolute, in those little bars, we have I minus n-1, and that really means raised to the power of I in reverse order. So if we start to loop from the last element, we're gonna raise to the power of the first element, the second element, and so on and so forth. So n is the number of symbols, a is the list of symbols which belongs to a base. So in case of 10, base 10 is gonna be from 0 to 9. In case of base 16, for example, is gonna be 0 to 9, and a, b, c, d, e, f, as we talked earlier. I know this was probably complicated, you probably didn't understand it, so let me go ahead and jump right into an example. So let's say we have the number in base 16, and that number is ABE. So how exactly we convert ABE to base 10? Because we said we want to convert from base n to base 10. We do that simple operation according to the formula which I showed you before. So basically we take the last number, which is 14. And why did I say 14? Well, 14 because E really means 14. So 14 multiplied to the base, and the base is 16. 16 to the power of 0. Why power of 0? Because we're going in the reverse order. So we basically have two directions here, and they both go in opposite directions. So the first directions go from the last element to the first element, and the second direction goes from the first to the last. We're going to have 14 multiplied to the 16th power of 0 plus 11. And why 11? Because B is 11 in decimal, multiplied to 16 to the power of 1 plus 10, which A is 10 in decimal, multiplied to 16 to the power of 2, and that is 2750. So let's say we have another number, and that is in base 2, and we want to convert base 2 to base 10, right? So base n to base 10 basically. So the number is 0110101010100111, and that is probably a very long number. So we basically apply the same operations here. So we start from the last symbol, which is 1, and we multiply it to 2 to the power 0, and then we do the same thing over and over again until we get to the last bit, which is 2 to the power of 15, and we multiply it to the symbol, and the symbol is 0, and eventually it's going to be 0. So if we sum up all these numbers, we should get 27,303. And I told you this is a big number. All right, guys. So another thing I want to talk about real quick is examples and conversions. So don't think you're not going to have something to work. And that work is going to be very simple because we explain what binary is, we explain what decimal, hexadecimal, all those number systems, and we also explain you how to do conversions. So right now, I'm going to show you some numbers on the screen. So basically, you're going to have to convert the number which I'm going to show you to two bases. So if the number is in base 10, you're going to have to convert it to base 2 and base 16. So if the number is in base 2, for example, you're going to have to convert it into base 10 and base 16. So here are the numbers. Take a small pause and solve these exercises. All right, guys, I hope this was not a big challenge for you. So let me show you the results. For the first number, in base 10, 115, we have in base 2, 01110011, and in base 16, we have 73. For the second example, 3AB in base 16, we have in base 2, 0000001110101011. And in base 10, we have 939. For the next example, which is 11110011, in base 16, we have F2, and in base 10, we have 242. For the next example, we have in base 16 FF, and in base 10, 255. And the last example, which we have ABC, it's a really long binary number, so you can check it out. And in base 10, we have 2748, which is a big number, as I said. So another thing I want to talk about are encoding schemes. So two popular encoding schemes which we have and which are widely used are ASCII and UTF-8. While numbers are good, we said that circuits are not so good, numbers are better. While numbers are good, we can't really remember numbers because we're humans and we forget things very easy. However, we like things to be semantic. So how exactly we map a character to a number, or how do we map a number to a character? And that work is done by encoding schemes. So one popular encoding scheme is UTF-8 eventually. So let's go ahead and dive into some details of ASCII and UTF-8. So basically, ASCII is a 1 byte representation. 1 byte really meaning that the values mapping the numbers to the letters numbers, or the characters, I should say, are ranging from 0 to 127, and that's a 7 bits representation, which was the first initial ASCII table. And then we got extended ASCII table, which uses 8 bits, and the value ranges from 0 to 255. Also, we have UTF-8 on the other side. So UTF-8 is a 4 bytes representation, and 4 bytes representation is a huge number, and it ranges from 0 to 4,295,000,000 and so on and so forth. I mean, it's a huge number, and 8 really stands for 8 bits, so it's a 8 bits 4 bytes representation, and it pretty much represents any alphabet in the world and pretty much any weird character. So let's go ahead and have some examples for encoding and decoding as well. So let's say we have the string hello, and that is already encoded, and we want to decode it. And to decode it, we just take a look at the table, and H really is mapped to 72, E is mapped to 69, L is mapped to 76, and O is mapped to 79. So let's say we have another example, world and exclamation mark. We could decode that very easy by having a look at the table, and it's really about that simple. So let's have a look at some examples and conversions, and here's the part where we're gonna have to do some work. So basically, I'm gonna show you some strings, and I'm also gonna show you their representation in decimal, so you don't have to dig in for the table, and you're gonna have to convert them to binary. So pause the video, take some time to knock this one out, and then come back to see what are the results. All right, guys, I hope that was not a big challenge for you, and you nailed it properly. Well, maybe except for the second example, which I put it on purpose there. So we have the numbers, and then we have the results, which are the following. And you may solve the first and the third one very easy, but you may ask yourself, why on earth the second example is represented by 3 bytes? Because it has 3 numbers over there, and it's really one character, but it's represented by 3 bytes. And we talked about that. We said that UTF-8 represents characters up to 4 bytes, so it's gonna use up to 4 bytes to represent any character in this world. All right, guys, so the last example I want to show you related to number system is a personal encoding scheme. While that may sound very weird, this is actually real. I mean, we use encoding schemes because we don't want to remember numbers. So I came up with my own encoding scheme, and this is called Steve Enc, which really stands for Steve Encoding Scheme. I know this is weird, but I just made it up for you to understand the concept. So let's say we have 2 values. We have Steve 1 and then we have Steve 2. So basically, those are the values which can represent a state, which can represent a binary state, which can represent on or off or something like that. So according to the table which I showed you before, Steve 1 and Steve 2, they can do one thing. They can either raise their hands or they can put their hands down. And doing that in a combination means something or another thing. So when Steve 1 puts his hands up and Steve 2 puts his hands down, or he is upset for some reason, it means bring some beer for Steve 1 eventually. So when Steve 1 puts his hands down and Steve 2 puts his hands up, that really means bring some soda eventually for Steve 2. So when Steve 1 puts his hands up and Steve 2 as well puts his hands up, it means they're both happy and they both want their drinks. So it means bring some beer and also bring some soda. You don't have to bring one or the other. You have to bring both. Otherwise, they don't satisfy. So when Steve 1 puts his hands down and Steve 2 as well puts his hands down, it means something bad happened. It means they are not happy and do not disturb them, or you may have some problems. So that's really a trivial example of how you can have your own encoding scheme and do encoding based on numbers, based on states. And that's really all about computers and how they work. So I hope you guys understood it and it was fun for you to learn with me. Alright guys, so if you like this video related to how computers work and number system, make sure to put a thumbs up. If you didn't like this video, make sure to put a thumbs down and tell me where should I improve. If you're also new to this channel, make sure to subscribe and click that bell button because you will receive notifications related to new videos which I'm about to make. So this was Steve. Peace.